Hello, everybody. So we're getting pretty close to the end now. The semester ends next Tuesday. So that's the final cutoff for everything is next Tuesday, 11:59 p.m. All of the assignments will close and lock. And then the following morning, next Wednesday morning, not 2 days from now, but was that 9 days from now? I'll wake up in the morning and finish up any grading that's left and submit grades first thing Wednesday morning. And I wake up early, so I usually have that done by like 7 o'clock the following morning. So please make sure everything's turned in by that final deadline, which is next Tuesday, not tomorrow, but 8 days from today. So getting very near the end. And as such, well, y'all probably remember back at the beginning of the semester, there was it seemed like most of our material showed up early in the semester. And that was by design, so that when we get near the end, there's time to focus on things. I got the final project, and then I think tomorrow, might be Wednesday, the final exam will open. And there's one section that has a bunch of questions, which are taken from the same question banks that your weekly quizzes were taken from. So if you've worked through the weekly quizzes, you've probably seen a lot of the questions before. And then the second half of that is writing a program. There'll be instructions for a small program to develop. That'll open up here in a couple days, and then there'll be 7 days to work on it before that deadline. That and final projects and any like past due assignments and stuff. The end of the semesters always get a little bit hectic. So I like to front load the courses. And that way, when we get to the end of the semester in classes like this, it's kind of some odds and ends. Just things that I think you will find useful. There's one more that I always like to cover, how computers track time, because it's not the same as how humans track time. I even put a requirement in the final project that you have to have some sort of timestamp in there. I can't remember how it was phrased. So that's on the to-do list. And then the rest of it is just some odds and ends that I think will be useful for some of y'all. And that's pretty much what our lecture is going to be the rest of the semester, is things that I think y'all will find useful. And yeah, the to-do list for today is much longer than we'll get through. And it's going to be like that Wednesday. And then again, next Monday, I'll have a whole bunch of things ready and we'll get through as much as we can. Because, well, like I just said, the big thing now is getting that work together. We've seen all the pieces. So now we have to assemble them into our own thing, that final project, and then catch up on past due work and all that. So I want to make sure there's lots of time for that. So my plan is to go 45 minutes to an hour, so probably an hour, then we'll take a break, and then 45 minutes to an hour. And so a little shorter than we have been doing. And that way there's lots of time in our scheduled block when I'll be sitting here ready to address questions that we can use productively and work on the final projects and anything else that needs done before the end of the semester. So I guess let's talk about that, just the odds and ends. So I always like to point this out. I pointed it out at the beginning of the semester and come back and point it out again now. If we go over to Ivy Learn and look at the syllabus, which most people probably haven't looked at since the first day of class. But in not just our syllabus here, but in the syllabus for every one of your classes, there'll be this section called Course Outline of Record, the official write-up of the course, how many credit hours it is, a description. And one of the sections in there is the major course learning objectives. So not just for this class, but in all of your classes at Ivy Tech, the syllabus will have this list of things you're supposed to learn from the course. And when the course is a prerequisite for a lot of other things, like this course is, when you get into those other courses that you're required to take this one first, they're going to expect that you know the things on here. So in all of your classes, as we get near the end of the semester, you always want to make it a point to look back at the syllabus and skim over the major course learning objectives and make sure you feel like you learned everything you were supposed to from the course. Because some of it might be important in next courses, but we kind of did a lot of this stuff. Flow charts and UML diagrams, describing things, basic logic structures. That's a complicated way to say selection structures, the if-else stuff, reading and writing files, some stuff about arrays and tables. They just wrote it in kind of a vague way, which is another thing about these major course learning objectives. They're often quite vague, so it might take a little bit of interpretation to think through and figure out if you really learned it or not. We talked about logic gates and set theories, the Boolean operations, things like that. Problem solving skills, that's pretty much what we've worked on this whole semester, is focus on developing algorithms through various little bits of practice, the Python in the textbook and the Raptor assignments. Graphs, charts, and tables. I think everybody knows what a graph and chart is. That's one of the things I was going to look at today. More focused than we looked at graphics earlier. Some more UML stuff, more about problem solving, the base numbers, we looked at that. A recent discussion board was about programming and scripting languages. There's one, we'll get there before long. Develop a simple program. We did a bunch of that. Different methodologies, like how we get a project done. What's the best way to do that? And we've kind of covered everything on our list here. I always like to front load the courses so that when we get near the end, we can just do odds and ends that will pertain to what people in the to your interest, things that you all will find useful. And well, hopefully find useful. That's why I put it on the list. But most of our time here at the end is going to be actively doing stuff, finishing up the work and all of that. So I just like to give that reminder. Make sure you check that in all of your courses, especially the ones that are prerequisites for other courses, because when you get to that next course, they're going to assume that you learned everything on that list. While I'm here, I sent out an announcement a few minutes ago. If you haven't seen it, the Tech Club for the School of IT is holding a LAN party this Friday, big game jam to help everybody relax at the end of the semester. So if you want to, if you're interested in attending that, there's a little flyer, attached to the flyer here, has information about how to register and all of that stuff. Spend the afternoon playing games, a fun way to unwind after a busy semester, or as we approach the end of a busy semester. And I already closed the flyer. That is both in person and virtual, right, Tyler?
Yes, sir, it is. We will be available for everybody, not just people going to Salisbury. We'll have in-person options and pizza at Salisbury. Unfortunately, we can't deliver to your house if you do virtual. But we have a Tech Club Discord server that I'm going to invite people in who are interested in the Tech Club. And for the Tech Club game jam, there'll be like a little channel group in there for anybody to join, and anybody can play together. So
okay, yeah, so you don't necessarily have to be near Sellersburg. There's pizza if you live near Sellersburg, but and come to campus, but you can stay at home and just participate with the thing. That's coming up this Friday from noon to 6.
Yep.
So there's a registration thing on the flyer.
Online too.
Oh, and with the registration, the form does collect the Ivy Tech email address. So make sure you're logging in from your Ivy Tech account. Your Ivy Tech account counts as a Google account. So if you're on Google Chrome, just make sure you're signed into Ivy Tech before going to the form. Otherwise, I think it might not let you in. A couple people had said they
Either
had-
way, I made it a requirement on the form to provide an email address. You can provide your Ivy Tech email address there. It's so we can email you the registration for the on Ivy Tech side of this. The form is mainly just to gather emails and preferences on food and drink and games.
Okay.
So,
Okay.
yeah.
Yeah. Okay.
Thank
Yeah.
you, Chris.
So all the stuff's in the flyer. Take a look over at that flyer if you're interested.
And if the QR code doesn't work, try putting it up on your desktop and scanning it with your phone. If that doesn't work, email me or Chris, and we just put it in the chat. I'll work on that right now, actually.
Your thing cut off a little bit. If you put that in the chat for anybody that's curious, that'll
Yep,
probably
I will.
be nice.
Yeah, terrible signal out here. My apologies.
Okay. Yeah, so I have a couple things on to talk about today. First off is how computers handle time. And then I want to take another quick look at graphics with something more focused in mind, the traditional charts and plots like we're used to doing, and just do a quick run through on a couple of those to see the steps that are necessary. Because you're probably used to things like Excel where we just click that chart button. But in a class like this, where we're talking about programming, we want to see at least a brief summary of the steps for making a chart. And then I got some other things that we'll probably see how far time goes. That might be interesting to some of y'all. So first off, does anybody know how computers handle time? Have you heard this before? Dates and times.
I think you mentioned something about it dating back to 1970.
Yes. So they needed a way to be consistent for all so all machines were consistent. So they just picked a day. And started counting milliseconds. And then if we have the milliseconds, we can find any of our other times, right? For example, if we know that 42,715 milliseconds have passed, we can divide by 1,000 to get seconds. So we'll take that and divide by 1,000. We'll get as seconds. Then if we take that and divide by 60, we can get minutes. Divide by 60 again. That doesn't look like 6. That'll get us hours. I ran out of room there, but I think y'all know where the pattern goes after that, right? Divide by 24. Divide our number of hours by 24, get how many days it is.
Yeah, just like scientific notation.
Yeah, we just keep going down to, we can turn milliseconds into any other one things just to set up the calculations for that. So we really just need the milliseconds. So when this started, we used the Unix epoch. That's when they first thought of this. And that's sort of our main one. So that is midnight on the 1st of January, 1970. So obviously they came up with the idea in the late 60s as networking began to grow. That was where it was a big problem, because if every computer was doing its own thing, it doesn't matter what the time is. But when we need computers to work together,
So I have a question.
synchronizing time becomes more important. What's that, Keegan?
So when you're mentioning time and everything, dates and time, like makes me think back to the moment where in history where is Y2K. Like I wasn't born, but why why were people, worried so
So
much
that was a
about
different issue. That
Y2K?
was getting into databases. And when they built a bunch of databases, they only left 2 digits for the year. So if something happened on, say, March, they put the year in like March 17th, 1988, they would just put 88 instead of 1988. Or, yeah, and then they only left enough.
So we
room
wouldn't know the
for
difference between
two
1901
digits.
and 2001,
But
right?
when we get to 2000, our digits roll over, right? When we get back to 2000, our year is 00, and then it starts over again. So if the business recorded something on March 3rd, 1988, and only used 2 digits, at least hopefully that business is still going to be running in 2088, right?
Yeah, it's just so, but for databases that had the whole complete year, like people were just like worried that
Oh,
that
so
when it came on, like the databases would shut down.
yeah, because all of our programs depend on those databases. So I said databases, but that would follow the technical definition of database, where like files are technically a database. It's a hierarchical database. We would never actually call it that, because even people that know that does technically fit the definition of database. If you called it a hierarchical database instead of a file structure or directory structure, people would look at you like you're strange. But whenever we stored the data, we did that. So that was the fix. They had to go back through all of the data and turn that into a 4-digit year.
Okay. And where would they store this? Where would they store this data of the dates and times?
Everywhere.
Oh,
Everything that had a date was like that, which is
okay.
why it was a worry, because when they realized it, there was only 5 years to do that, and they had to go back through 70 years worth of data and manually change 70 years worth of data.
Yeah, that must have
In only
taken
5
like
years.
that took a while.
Yes. So there was worries about whether it was going to get finished in time. But
Yeah, and plus, it would mess up the whole world
yeah.
time, because the world has different time zones. You got to have computers that adapt to those different time zones, like
Oh
like
yeah. So that relates to
time.
the Unix epoch. That's Paris Universal Time. So at midnight in Paris on January 1st, 1970.
Yeah. So there's just like multiple time zones, and so you gotta program a system where it can adapt to all sorts of time zones.
But even before computers, there was still that problem. So we used Paris. Also,
yeah, so there's
What
just a
about the
universal
median
time where
time?
people
Yeah.
agreed on. There was a universal time where people agreed on, and it's like, hey, like here's less hours here, or you gain couple hours when you travel here, or
oh yeah. All of that set up. It was set up rigidly long before computers. But
and
yeah,
then
I guess in the time zones.
yeah, and then how did that system was ingrained into computers and the
That's
systems that we
interesting.
know today?
computers just measure milliseconds. That's what I was trying to describe now.
Okay.
So
They measured the
we
time
take
zones
the starting
differently
point.
with the milliseconds too.
Everything's measured off the metric system. All of that. There's still a few. Some of our measurements are real now, but in universal standards. But a few things are still kept in a vault in Paris, like the weight of a kilogram. We haven't found a universal standard for that. So there's a chunk of metal sitting in a vault in Paris. Also,
cool.
in that same building, just down the hall, is the clocks that every other clock in the world synchronizes to, which is one of the problems with the Unix epoch.
So why is it like, so why is it Paris? Like, why is the designated universal time?
That's
Like,
where all of our measurements are stored at.
oh, the measurements, like what we get today of like systems and measurements,
Yeah,
like
the 0
grams
degree,
and-
on the map.
yeah,
Paris. Also through a suburb of London, but it makes more sense to say Paris because that's a bigger, well-known city.
yeah.
That's what
Plus,
I
it's like
thought. It was some in
it's the
London. Is it
epicenter.
Meridia or something like that? Am I a robot-y? I probably am.
Oh, yeah. Greenwich. It's
Greenwich? Thank you.
yes. Yeah, Greenwich, England. It's just outside. It's probably in London these days, but it was just outside of London when they did this.
Okay.
All of this was set up before America. We just had to measure everything out of Paris, of the line that goes through Paris and Greenwich and London, even before America.
The only thing they could agree on.
Mhm. Yeah. So that's where we're measuring, and we just measure milliseconds since then. But there's a problem, and that's there's a finite number of milliseconds we can hold, right? Finite number of milliseconds. I'm just going to write MS there. A finite number of milliseconds a computer can hold. And hold as an integer. Actually, I'll put down with this as a long integer. It's a 64-bit number. So when we were looking at binary code, we looked at 8-bit numbers, and we can get up to, well, from 0 to 255, 256 values, but we have to include 0. As we add more bits, every time we add a bit, that doubles. So it's a really big number. Let's just pull it up on Google real quick. Biggest number in a 64-bit integer. So it's a really, really big number, right? But it is a finite number. Where are we at here? So there's thousands, millions, billions, trillions, whatever word comes after trillions, and then whatever word comes after that, we have just over 9 of those. So there's a lot of milliseconds, but milliseconds pass quickly, right? So there is a finite number. So that's the first problem with this, is that eventually it will run out. So I'm going to write a 1 here. Eventually we'll run out, and we'd have to reset it, which
by the way, you were saying what is past a trillion? There's quadrillion and then there's quintillion.
okay, so yeah, so we only have 9 quintillion milliseconds. That's a lot. That'll take us up for a while. Eventually it'll run out. In particular, it's going to run out at some time in October of 2038.
That's the when you're speaking of 9 quintillion, that's like around the same odds of a Rubik's cube being solved.
Yeah,
You know,
There's
with
a lot
I
of
mean, like not solved, but like all the combinations is the same thing with those 64. What's the largest 64-bit integer?
yeah. It's not really a coincidence, but we get into high level math.
It's
to answer that
crazy. Like
question.
it's so similar. Like there's like, you know, 9 quintillion ways, you know, for combinations on a Rubik's cube. And then with those 64-bit integers you were talking about, like, you know, since there's only a finite of them, like
Well, it follows directly from something.
exactly.
How many how many faces do we have on each side of a Rubik's Cube that can move? Well, there's 9 on each side, right?
Yeah, there's 9, yeah.
But that middle one can't move. So we only have 8 that can move on each side, right?
Yeah.
And then to move any particular one, we basically can do that, right? Spin it.
Yeah, we can do that like north, south, and then east and west, and just go on
Yes.
those directions.
So there's 8 squared or 64 things we can do to each face of the Rubik's Cube. And then when we do that, we end up with 2 to the 64th power possibilities. So there's the exact same number. There's from that number we just looked at, the possibilities on a Rubik's Cube would be 1 more because we start counting at 1. We don't say there's 0 things we can do with the Rubik's Cube, right?
Right.
To not do anything and just set it back
That's
down.
incredible.
That's one thing. So we start counting at 1 instead of 0.
But did I use a good analogy there of what we're talking about today of Rubik's Cube? And
That
Made
was
some gears go
a
on
little
there.
sidetrack from a coincidence, but it is not a coincidence because it's 2 to the 64th
Fascinating.
in both cases.
exactly. And plus with like, bits of information, like there's only like a possible number you will get to before it like
Yeah,
runs
it's
out.
finite. It doesn't go on forever. Like, we can't say there's always more.
Yeah,
To
we
get back
can't,
where
and
we
plus
were,
we can't store like
if
multiple.
we're counting milliseconds, eventually we're gonna run out, right?
Exactly.
And
Even
then this
time.
is one that surprises most people. The second problem is, well, we should be able to, seems like we can easily do some math about time, right? But I just left a blank here when we're gonna run out of that. Because it kind of surprises a lot of people. We're not exactly as accurate as we think we are for predicting time. Well, I was just gonna write one more word up here. There's a problem that we can't say exactly when we're gonna run out of because of leap seconds.
And to you, like what's easier to predict, predicting time or predicting events?
It depends. That is a very large rabbit hole to go down. So let's not take that rabbit hole right now.
Okay.
So
Like,
there's something with time called leap seconds. And we can't really predict leap seconds. We can measure, we know how to measure them. So we know when those ultra precise atomic clocks in Paris get off. And whenever they do, whenever we measure one, June 30th becomes 1 second longer. So we have to add a second back in. Or sometimes we have to take one away, which prevents us from giving the exact time that we're going to run out from the Unix epoch, which causes a problem. Because if everything was going to run out at the same time, we could adjust for it. But to get around both of these problems together, they just added more epochs.
And with that on a computer, right? Like where does the lost seconds go?
The computer's resynchronized to the clock in Paris. We don't have every machine doing this.
Right.
The machines just ask the clock in Paris what time it is.
Right.
And then they base it off that.
And then it keeps track of whether to add or move a
Yeah,
second.
when was the last time you set your phone?
The last time I set my phone.
Or set the time on your phone, right? All we do is turn it on. And if a couple of our clocks are off, they'll resynchronize before long across the network.
Yeah, so just like setting an alarm clock. I set an alarm clock for things.
Oh, well, I meant the time.
Oh, to set the time. Yeah, my phone does it for me.
Yeah, all of our machines do. So we don't have to worry about that part. We'll take small measurements following the same way.
Except for the car, except for, like our cars, it's like for some reason it doesn't like
Because they're not
adjust.
networked.
It's not networked.
If you had a Tesla, it would.
Oh, of course, a Tesla. Thank you, Elon Musk.
I think the new electric Mustangs do. But I'm
Oh,
not
they
positive
do. They
about that.
adjust. They adjust the time.
Yeah,
Because with
eventually all the cars will, but not yet.
yeah, so just like traveling to different time zones and everything, like it could be quite kind of confusing when in
It
terms
shouldn't
of
be because when your phone, like on your phone, when it notices you cross the time zone, it'll change. If you go from
yeah,
here
and
to
then you could
Chicago,
just
your phone
then you
will
could just
change
adapt your
to
then you
Central
could
Time.
just adapt your phone to it, or you're not your phone, but your car to it. Yeah.
Yeah. So back to this, we had a couple problems, and to get around that, especially where it's going to be overlapped, we just made several epochs. I'm running out of room. This is the very last thing I was going to write on the board. Different software goes off a different epoch. So they don't all go off 1970. For example, the example we're getting ready to look at to see bringing this stuff into code using Raptor, it uses the epoch in 1990. And that way they don't run out of time at the same place, right? A software written with one on the Unix epoch that runs on 2038, and another piece of software that written with the epoch in 1990, they can resynchronize afterwards. After one of them runs out and has to reset, there's time to resynchronize those. So that's how computers measure time. It's just the number of milliseconds that have passed since a certain epoch. Unix epoch is the official one, but there's lots of them scattered around. And then, like Keegan just pointed out with cars, the machines are constantly resynchronizing themselves. And leap seconds cause a problem because all we can do is measure those. We can notice when we've missed a second, and then June 30th becomes a second longer. Or
Yeah,
we notice,
good thing we have the technology we have we have today with phones and everything, since I could imagine just changing the time back on certain things back then, like old microwaves, and like they have that like certain times on them, and it's just like
it wasn't that difficult. It was like resetting a clock after the battery dies. It doesn't need done very often.
yeah.
How often do we go down? Do we worry about the exact second? Right? We look at the clock and say, okay, it's going to be 1 o'clock in a few minutes. We don't really, or right now we look and say 1:30.
Right, I get your point.
We don't say 1:33 and
yeah, I get your point.
Before I even got the number of seconds out, right?
I just get your point. It's just that with just with technology, it's just like people.
It makes it easy. It makes it easier. But yeah, there's a lot of details going on behind the scene, because we've seen about programming to all of that stuff. Setting that up has to be done in small steps along the way. So if we're going to use this in our program, that's a little bit easier because it's set up in the background. We just have to know what it is to use it. So I'll open up Raptor here and bring in a couple numbers. So it's built in to just grab the stuff. So I'll set something to now. And in Raptor, if we start typing current, you'll see down on the predictive list here, there's a whole bunch of different options to get. So basic one is current time. And well, I'll just use the watch window. Well, maybe print it. Print now is plus the variable just grabbed. And then make this really wide. Maybe clear the console before I print. So there's the milliseconds. couple years ago when teaching this class, I couldn't tell exactly which one that, I could tell that wasn't the Unix epoch from 1970. So I punched it in a calculator, and that is January 1st, 1990 is the one Raptor's using. But it is milliseconds. So as if I do that again, it's like the next line of code, and see 20 milliseconds passed running that code. Or if I turn the speed down, even more milliseconds will pass. So we get the current time, print that out. Looks like this time 100 milliseconds passed between those. So that's the ones that
Now,
those are the one, those are our actual times. So when we want something to happen, like we want to wait for a certain amount of time to pass, it's best to use two numbers like that. So I'm gonna take out those print statements and just kind of change this. I was just printing it out. Instead of calling them now, I'll call this like a start time and an end time. Is, well, we saw earlier, we can put a computer to sleep. For us here, it's just delay for and so many seconds, 0.3 seconds. But the problem is when we delay, the program can't run anything else. The machine just stops there and doesn't do anything else until that amount of time has passed. Oh, save. So a better way to do that is to maybe like in a main loop, we can keep looping until a certain amount of time has passed. Whoops, I didn't mean to do those. So I'm gonna grab this end one here. So we'll go in here and then we can see how much time has passed. So like if end minus start, whenever we do changes, you always want to do the later minus the earlier. That way a negative number would imply backwards in time. But usually our later time is going to be a bigger number. So we'll subtract that. So if that's been more than, say, I'll put 345,000. Oh, 3,450. That's 3.5 seconds. We can keep doing stuff while that time passes. I'll just print still waiting. And after that amount of times, like that's about 3.5 seconds. So the big difference there is if we delay, if we said delay for 3.5 seconds, it just stops. Actually, I could put that in here. Delay for 3.45 seconds. And then when this is running, how's it not running? Try that again. It hits that delay for and it just stops. We can't do anything else. I'll slow it down so we can see the boxes. So you see it hits that block or that instruction and then doesn't do anything else for however long. So a much better method than putting the computer to sleep is set up a loop and just take your time measurement. How many milliseconds? What's the current milliseconds? And then keep checking over and over again. And that way we can keep doing stuff while the computer's looking at those milliseconds. And eventually that amount of time's passed and it just moves on, which will be a lot more print lines if I turn the speed way up. go back up to full speed. And the computer was able to do all of this stuff, which I am scrolling here. We can't really see it. The computer was able to do all of this stuff, run 456 instructions, basically. How many do we have to take off there? 1, 2, 3, 4, 5, 6. So if we take off the other 6 blocks, the computer was still able to do 450 other things during that time interval instead of just going to sleep. So that's oh, make that smaller, don't I? Cut that and make another, move that over to a subchart. Call it do not sleep. Maybe spell that a little bit better.
I have a question.
Yes.
So we did that one in a loop symbol, but is there an easier way where we don't have to do a loop symbol to calculate the start and end time?
Well, that's just 2 numbers. You mean like right here?
Yeah, just without the loop structure.
We could do that calculation anywhere.
Oh, we can?
Yeah, that's just subtracting 2 numbers. That's all we have to do is subtract 2 numbers, but is that what you're asking?
Yeah, I'm just asking, like, is there a, simpler way to do these things?
This should be the simplest way.
Okay.
Because we have to keep checking, right?
Right.
The alternative would be to do that calculation thousands of times. Keep
Okay.
doing that calculation like every line of code until we get to it.
It's just I'm still learning about these things. And so
Oh.
I just like,
So we want something, we want to do that over and over and over again, right?
right.
So we either have to write that line every single time, which we might not know how many times it's going to happen, right?
Right.
This time it happened 450 times, but if I turn the speed down, oh, well, I have to call that method. Let's call that method. And turn the speed down, and now it now it only happened twice. So without a loop, we wouldn't know how many times to write that instruction, because it depends on how much there is to do in things, right? It's how long it's going to take. So a loop would be the easier way to do that. In general, that's just a better alternative than telling your computer to just stop doing anything for so much time. That way you can keep doing things.
Yeah, so no delay. So just,
Yeah. Or during the delay, the computer can do other things.
right.
You don't have to stop processing for that amount of time. Otherwise, our other ones on there, we would type current minute. What? Okay, apparently I can't use the word min. That's reserved elsewhere. But grab the current minute.
That's because they already have min for like a minimum.
Yeah. Yeah. We can't. Certain words are already being used. So you can see there on the screen share, the clock here on my computer says 44 or 45 now, but that's the number that one grabbed. And all of our stuff will be that way. So like, what else do we have? Hour to current hour. Um,
Can we put that like before the minute?
oh yeah, I was just gonna grab all of them. So like
Okay.
second to current second. I was just quickly going over the syntax to show you where they are at. Is that would give us enough to print out the time, right? Then we can print hour plus a colon plus our minute plus I'll do 2 a colon plus our second. So all that should look familiar. Once we have the numbers, we can just concatenate up together a string. And you can see that gives us the military time. So might need to make little adjustments. Whoops. Let's use regular time. So if our hours is greater than 12, then we want to subtract 12. Hours is going to be whatever was stored in hours minus 12. And then our clock can show the regular time, or we can put in what in America we call military time and what the rest of the world calls train time. It's like train schedules and bus schedules and boat schedules, and all of the mass transportation things run on the 24-hour clocks in the rest of the world. In America, it's just confusing. Uh-oh. That's supposed to be hour. Things moved on me. So just little checks like we're used to using. So, once we have those numbers, you might have to do a little bit of manipulation to put your stuff together. Where did I mess up that word? Oh. So the variable hour is going to be whatever was stored in hour, and we'll subtract 12 from it. So it's kind of like that increment decrement thing. It shows up a lot, right? The value we want to store in that variable refers to the old value that was there. So the same name shows up on both sides of the expression. Our instructions when we type code, actually, they always run right to left. So it kind of confuses people at first. I'll just mention that, but the fact that this calculation will work shows that things always run right to left, not left to right the way we type them. So then if it's the middle of the afternoon, we get that, or when it's early in the morning, which I can't really change this time on my clock to at least not easily.
How can we train Raptor to, have like, not just to get one time, but like to continuously go,
Oh, yeah, you just put that in a loop.
Yep. Just like we did with the last one.
Yeah, let's add milliseconds and then just make a clock here.
Yeah, let's just make a clock.
Millis to current millisecond. Might as well. That's a good place to see all of them, right? And then we'll concatenate on. I'll put 2 colons before the milliseconds plus millis. Then might as well add a date to it.
When you have
as
to
well.
do it with the other one on the other output.
What's that? I couldn't hear you, Keegan.
Oh, when you have to put the millis on the other one where it says no. So you already have that.
Oh, yes. Yeah, I was thinking we wouldn't really see that this time, so I was just looking at the S branch. I'd have to go change my clock and tell the clock I'm in, where's it morning at? Siberia or China is morning right now. So I'd have to tell the clock, my computer, it's on the other side of the world. So that'll give us the current time. And then we would just do that over and over and over again. I just put no here. Nope, it's not going to let me do that. One is greater than 3. So that'll always be false. So it's just going to always go into this loop, right? I have to zoom out to copy and everything. I can grab all this stuff. And then we just do that over and over and over again. And that's all it takes to make a clock. Turn the speed up so that we get more results, but for our purposes here, really on a clock, 1 second would be enough, right? So it just keeps giving us that time. And yeah, we could put in that condition like we did earlier to wait to check the time until 1,000 milliseconds have passed. And that way we're only checking once a second. Eventually it'll roll over to 152. I guess we can see it's going up, but
I want to see if it goes on to 152.
yeah, it'll reset because it knows how many seconds there are in a minute. So almost. This time it'll be 152. Yeah. So you can see our milliseconds aren't passing 1,000. So if we say current milliseconds, that's like the clock on the computer.
Right.
Same with hour, second, millisecond. And yeah, we don't need to sit and watch a clock forever. So I'm going to cut that and put that on a subchart called clock. Yeah. Which we could also draw, right? We could take those numbers and use those numbers to draw lines and circles under a graph window and have the other window because we have all our numbers. So then it's just a matter of doing the calculation for where our particular line needs drawn every second of the day to make a full clock. That'd be a fun little project, practice drawing with the computer. Some of our other ones I wanted to make sure and look at. Make this big enough y'all can see it again. Because we also have things like day is current day. I'll just print it out. It's a plus day. What do y'all think this is going to give? Any guesses?
Ooh, what is the?
I mean, Monday, right?
That's what it should give. Oh, it gives the date when we say day.
So it's in that. Okay. Haha. Good trick question.
If I start typing day to current, if we look at our predictive list down here, day, hour, millisecond, minute, month, second, time, year. So it looks like we don't really have a good way to get a Monday on this one. There are ways, but it's not really, it's not necessarily built in. What else do we have? Month.
Well, that'd be a cool program, determine the day of the week by.
Oh yeah, it's an easy calculation. Just Google the calculation. Formula to determine day of week by date. It's actually a neat little hand trick. You can use
that's
your
neat.
fingers to do that.
You can use your hands for a lot of math.
Yes.
It's more than just your digits. It's you can count your knuckles, you can count your on and offs with your knuckles. It's really fascinating.
Somewhere
You can
there's
count
a
different bases.
calculation to do it. Function to determine that. There we go.
This is a cool book I read. I think that you'd like, Chris. I'll
Yeah,
try to
so
find
here it is. So we do all of this stuff. Century, year, believe K is the day. That's the only one missing here. The month, all of this stuff. And then take that mod 7 because there's only 7 days. You can probably find that written out a little bit better if you just do a quick Google search. Yeah, and then well, y'all can see where this is going. Year is the current year. What else do we have? Day, hour, millisecond, minute, month, second, time, year. And then we can print out some sort of message, right? Today is, I'll do it American style. Month plus a comma. Oh, wait, no. Month plus a space plus day. Then we put the comma plus our year. So there's where we get the timestamps. But you'll notice something about the month that might seem a little off. I'll check that out. Link to a book in the chat room. So
Oh yeah, it's really cool.
Normally, if we'd write the date, we'd say May, right? If we're going to use numbers, we'd probably use slashes or dashes. But we can
Is
do
a fake
a selection
fantasy
structure
calculator for my game.
What's that?
Can I use like a fake like fantasy calendar? You know, in Skyrim they have like different names for the days and stuff like that, just for like an immersion thing. But it's still a timestamp that's required, but it still has a little bit of flair. Would that be okay?
Yeah, that'll work. As long as
Okay.
there's a timestamp in there somewhere.
I was just thinking like, I just don't want, since it's a role playing game, I'll just say, oh, today is, but it'll directly translate to the, it'll be obvious.
Yeah. As long as there's a timestamp in there somewhere, because it's kind of an important thing. We need to be able to work with time.
Yeah.
You could also, it would be enough to do that time interval like we looked at. Like make sure a certain amount of time has happened before things have happened. What else?
That's true.
Month is
maybe a beat before something happens.
Yeah, so I think you all see where this selection structure would be going. It's going to take a moment to type it all up. Maybe if I copy these two and scroll over. Well, I'm just going to jump to the one that's going to give today's date. I think y'all see where to type, how typing all this in would go. If month is 5, then we'll say it's May. Since it's only going to give us today's date, we don't really need to worry about the others, but make that a little smaller. But if we wanted to go from the number into the word, we would just have to set up a selection structure. Because once again, once we have that number, we use our regular tools to adjust things and do the processing we need to get to that final result. We don't want to say 5/9/2022 in a sentence. When we put that in a sentence, we want to say May and use the actual words. So that's the basic idea of timestamps. Might as well show this real quick before we take a break. I'll just open something with Python. In Python, we have to import a module called date time. It's another one of those things that's already written, but it's not included by default. And then we can like look into that library, the pre-written code. And this one might seem odd. There's another thing in there called date time, same name as the other one. And then something like now gives us our current date.
Quick question.
Yes.
So when in the IoT lab, we had to code the GPIO pins.
Yeah.
For like an breadboard and stuff for like an Arduino. That was in C+, and that didn't have an import time. Like you could set the delay, but well, I didn't go deep into it, but I was thinking with the Python way of doing it, you need to import time, right?
Yes. In Python, you have to
Okay.
import time. It's a specific library in Arduino that's already there.
Okay, I understand.
Actually, I
And
have it
that's
on my
written in
computer.
C++?
I can point you towards it. I was wondering if you were going to do more than that.
Oh, I did. I did a little, like you can look at my assignment. I did 2 buttons and 2 lights and made them do different things. So I
Okay.
thought it was really cool. Yeah.
Um,
I'm surprised it was in C+ instead of Python, and that's why it threw me for a loop when I was first coding. And I was like, wait a second, that's okay. Yeah.
okay.
So
So
then,
yeah, whenever we write in the in that stuff, there's some code already brought in for us.
yeah, that
Particularly
was
this
actually
one.
really neat. It made things a lot easier.
So yeah, that's why Arduino took off, because it is so much easier than doing port manipulation. Without using the Arduino library, we have to go in and actually manually say what bits go into which register.
And to reinforce something in my brain, the Arduino library is also its API, right?
Yes.
Yes. Okay.
Okay, so it imports the it's one of those, either standard library or standard arguments. I can't remember which one. I haven't done anything in raw C++ in a moment. One of those has dates built in, has the times built in.
Okay.
So it's just already imported. Yeah.
Thanks for working through that with me.
Yeah, without that, we have to do things like do I have it on here? I put together some reference material because I very rarely do it in Arduino, but our code looks more like this. We have to say put a 1 into slot 7 of this register. Digital output, one of our digital output registers. Or here, put a 1 into this register. I think that's the 3rd slot over. So we have to manually control every single 1 and 0 going in there. Or well, I'm looking at this, it's going to look very complicated, but do I have any zeros? Oh, here we go. So this one looks a little bit different. Whenever I'm coding like that, dealing with binary directly, just to point this out, this is going to look confusing, but here is saying put a 1 in whatever green was. Maybe I should have looked up at the top. That's just a variable holding a number somewhere between 0 and 8. But that's the column, like when we were looking at the binary numbers, the power of 8, that column in a particular byte of data or the register size. So maybe that's a 3. This is saying put a 3 or 1 into our 3rd column of that byte. And here is saying put a not 1 into the 3rd column. So whenever I'm doing that, I don't think 1s and 0s. I think 1 and not 1 the whole time. But without the Arduino library, that's what the port manipulation stuff looks like, which probably looks very, very confusing, but just to show you all that and show that typically when we're working in that directly, we don't think ones and zeros. We think
On and
one
not
and
on.
not one. We think on and off. More directly on and off than 1 and 0. Those are just symbols that are easy to write. But our important thing here is these ways to measure time. So I'm going to put this in the chat room. Save that. And in the chat. And time. So if y'all want to download that from the chat, it'll give you some reference materials. So that is one of the requirements on the final project, is include some sort of timestamp and work with time in some fashion. So even if you just need to work in a delay or something, that would work. But there's also like a little help menu requirement. So you could put a timestamp on the help menu or something if you can't think of anything else. Maybe just spit out the date, what time it is, and somehow work a dates and time stuff into the final project. Because it is an important one if we're going to be working with computers. We need to keep track of when we did stuff, how long ago something happened, that sort of thing. But that brings us up to probably a good stopping point, maybe a good spot to take a break. Does 10 minutes sound good to everybody?
Yep.
Sounds
All
good
right,
to me.
so it's 2:06. So we'll get back to it at 2:16. Or if you want to write a quick program to count 60,000 milliseconds. No, that would be 1 minute. 3,600,000 milliseconds would be 10 minutes. Is that right? 3,600 times 1,000. Yeah, 3,600,000. Count that many milliseconds until it passes. Y'all know how to write those programs now, but I'll see y'all in a few minutes. We'll get back to it at 2:16.